Hello and welcome to lecture 60 of the course Computational Complexity. In the previous lecture, we saw interactive proof systems where the verifier is computationally bounded. He is a polynomial time verifier but has access to randomness, and the prover is all powerful. Right? We saw that graph non-isomorphism is an IP, which was a language that we did not know to be in NP. Right? So we want to know how big IP is. We already saw that IP is contained in P space, even though it's not a formal proof. I just mentioned as a brief remark. So in this lecture, we will see that sharp 3 set is contained in IP. Right? So as we already know, sharp 3 set is Sharpie complete language, and it is by Toda's theorem, it contains all of polynomial hierarchy. So interestingly, we see that sharp 3 set is an IP. Sharp 3 set as an interactive proof system. So just to recap, completeness and soundness. Completeness corresponds to the situation where X is in the language. Then there should exist a prover that can convince the verifier to accept with probability at least 2/3. And soundness is when X is not in the language. No matter what the prover tries to do, no matter which prover shows up, they should not be able to convince the verifier to accept the string beyond a probability 1/3. And as we saw, this 2/3 can go up to 1 minus 1 by 2 power some constant, and this can go up to 1 by 2 power some constant. So basically, and in fact, this is just by boosting, repeating, and doing Chernoff bound, taking the majority. And we also said that the perfect completeness, we can push the probability of 2 by 3 to close to 1 or exactly 1. Anyway, in this lecture, we will see that sharp 3 set is contained in IP. So basically, we will provide an interactive proof protocol where the prover will be able to convince the verifier, a polynomial time verifier, to the number of satisfying assignments of a 3-set formula, Boolean 3-set formula. And interestingly, this will also be a public coin protocol. So the protocol that we saw for graph non-isomorphism was a private coin protocol where the verifier did not reveal the randomness to the prover, but this will be a public coin protocol. So what's the problem? 3-set is given a formula, 3C in a formula phi. How many satisfying assignments are there for phi? Right? So instead, we'll slightly tweak the problem. We'll look at the decision version, even though I just formally stated now, but later I will not be may not be so careful. So given phi and a number k, we are asking, does phi have exactly k satisfying assignments? Right? This is the question. So this is a decision version. So the prover's task is to convince the verifier that this formula has exactly k satisfying assignments. And we have seen many of these, some of the ingredients of this proof in the previous lectures. So I may, when they show up, I'll probably remind you, right? So what is the 3CNF formula? So phi is a conjunction of clauses or an AND of clauses. Phi is C1 and C2 and so on up to Cm. There are M clauses and N variables, right? M clauses and N variables, right? The variables are x1 up to xn. Now, so let's try to, because we don't know any otherwise, let us try to see how this proof will go, right? So verifier may ask, tell me how many satisfying assignments are there. Prover may say it has k satisfying assignments. So now verifier, okay, now tell me, convince me that there are k satisfying assignments. So how will he convince, right? So there has to be a protocol, right? So some partial information or some specific information could be provided that the prover could, that the verifier could verify locally, right? So for instance, one possibility is this: verifier could ask, suppose I set x1 to be 0, how many satisfying assignments are there in that Boolean formula. So which is this, where phi, that x1 is set to 0 or false, and the others remain variables, right? So x2 and x2, x3 up to xn could take 0 or 1. How many satisfying assignments does this have? What if the prover can provide this number? Let's say prover says that this number is k0. Similarly, the verifier could ask how many satisfying assignments are there for phi of 1 x2 up to xn, right? And prover may say this has k1 satisfying assignments, right? So now we know when x1 is set to 0, there are so many k0, and x1 is set to 1, there are k1 satisfying assignments. Okay, and now the total number of satisfying assignments should be the sum of these two. So verifier could possibly check whether k is equal to k0 plus k1, right? And if k is not equal to k0 plus k1, right, then verifier can immediately reject. But suppose k is equal to k0 plus k1, right? So now what next? Well, one thing that could be done is so it is possible that if k is indeed the actual number of satisfying assignments, then and k0 is the actual number where x1 is set to 0 and k1 is the actual number where x1 is set to 1, then everything is being done truthfully, so it's all fine. But what if the actual number is not k? Let's say the actual number of satisfying assignments is not k. Now what does this mean? But k0 and k1 are such that k0 and k1 is equal to plus k1 is equal to k, right? So let's say, for instance, let's say there are 100 satisfying assignments, 40 when x0 x1 is 0 and 60 when x1 equal to 1, right? So maybe I'll just write them by the side. So 100 satisfying assignments, 40 when x1 equal to 0 and 60 when x1 equal to 1, right? So this is k0 and this is k1. Now let's say the prover says 100 satisfying assignments. Now verifier asks what is how many when x1 equal to 0 and how many when x1 equal to 1. Now verifier checks, maybe there are only 30 satisfying assignments when x1 equal to 0, okay, and okay, so he outputs 30 k0, but then the actual number of satisfying assignments when x1 equal to 1 may be something else, maybe that's also 30, right? So because then 30 plus 30 equal to 60, that's why 100 is not the actual number. But then the prover is trying to convince the verifier that there are 100 satisfying assignments. So what does he do? He could possibly lie and say there are 70 satisfying assignments when x1 equal to 1. So this is a lie, because he just wants to say it is 100, right? So this is something that can happen, right? Or maybe both of them are lies. Now how does the verifier catch this, right? So in other words, there should be some way. So these numbers itself may not be the actual numbers. So how does the verifier catch this, right? So one possibility. So let us see now how this could unravel. So as I said, like k0 and k1, there is a number of satisfying assignments when x1 equal to 0 and number of satisfying assignments when x1 equal to 1 respectively could be asked. Maybe we could recurse. So perhaps we could ask now to verify k0, right? We could recurse. So we could ask what is the number of satisfying assignments when x1 equal to 0 and x2 equal to 0, and what is the number of satisfying assignments when x1 equal to 0 and x2 equal to 1. And this may be k0 and this may be k01. And similarly, I could have k10 and k11. And then the verifier, and these numbers are provided by the prover, and then the verifier verifies that. Verifier checks k0 is actually k00 plus k01, and over here he checks that k1 is equal to k10 and k plus k11. Right? This is something that can be done. And now we have the same problem with k00, k01 and so on, k10, k11. But then you can see that the number of items to check is exponentially increasing at each step. And at the end, this leads to 2 power n many options, right? So basically, this just boils down to checking all the assignments, right? So this is not really that clever or anything. We are just exponentially many communications. All the numbers need to be sent. So at the end, we are just it's perhaps even worse than trying out all the 2 power n possible assignments and checking whether each one of them is satisfiable. So this is not efficient, right? So this is not efficient. So the verifier will need to check more than polynomial many things, even though this may be correct, perfect completeness and soundness, right? So this is not efficient. So this is clearly not feasible. Let's try something else. Okay. So instead of checking k0 and k1, one possibility is you just check one of them. Okay. So as I said, so maybe k is 100 and k0 is 30, or k is reported to be 100. Let's say this is reported 100, and this is k0 is reported to be 30, k1 is reported to be 70. It is possible that k0 is like, so it's possible that some of them are correct, some of them are not correct, right? So instead of verifying both, so earlier we just said that we verify both. So in this, another attempt is to, you just pick one path and verify that. So we don't check everything, we just check one path. And how do you verify k0 is 30? You again ask what is k00 and what is k01. Okay, I'm not writing them in detail. This is when, okay, so I'm not writing them here because there's not much space. So you just check sorry, there is some problem. Okay, so sorry, k01, you can check that. So k0 is you can ask the prover to give k00 and k01 and verify that. So here we verify that k is equal to k0 plus k1, right, here, and here we verify that let's say k00 is equal to k, I'm sorry, I'm having a bit of trouble erasing stuff. Not clear why. Verify that k0 equal to k00 plus k01, right? And every time we just choose one path to verify, right? So maybe over here we will check again k01, we will just check this path. Right. So this path, which path to be verified may be chosen randomly. Right. So so initially we have to verify k, then k0, then k01. So at every level there is only one item that we are verifying. Right. So this seems okay because we don't have an explosion of paths, because every level we are only verifying one item each. So there are n items, so there are maybe 2n rounds or something like that. But there is a small issue with this, right? So if the prover is an honest prover and he has the honest correct thing to verify, k being the actual number of satisfying assignments, then it's all fine. However, let's say this this formula has actually 90 satisfying assignments. Okay, actually 90. And it has 30 when k is equal to x1 equal to 0 and 60 when x1 equal to 1. Okay, 90 and 30 when x1 equal to 0 and 60 when x1 equal to 1. So which means k0 is 30 and k1 is 70. So the verifier, the prover could be very smart here. he could report K0 as 30 truthfully, but then his goal is to convince that K is 100. So if he reports K1 to be 60 truthfully, then he will be immediately caught. Right? The verifier can check 30 plus 60 and see that it is not equal to 100. So he will be the prover will be immediately caught. So instead, he can potentially lie, right? He can lie and say 60 instead of 70. Right? So can lie in one of this. Now, if in the next round the verifier chooses to verify, so in this attempt we are only verifying one path, right? So suppose the verifier decides to verify the correctness of case 0, then the prover has no problem, because at this point the actual case 0 is actually 30 and the prover has reported 30, so he can actually convince the verifier honestly that the K0 is equal to 30. So there is no issue with that, right? But there is an issue if the verifier asks the prover to verify 70, but when the actual number is 60. Now again, suppose K01 is actually, let's say, 25. And this number is 45, right? And sorry, this is this is a lie, right? So we said it is 60, so this is actually 35. Now let's say the prover decides to say K11 correctly, and he decides to lie here. He says this is also 35. So basically what I am saying is that at every level he can choose to lie in one path, because if he says the reports the correct numbers 25 and 35, he will be caught, because at this point prover will check whether 25 plus 35 is equal to 70, at which point prover will be caught. Verifier will check this. So instead he lies in this path, and he will not be caught if the if the verifier decides to go by K11 instead of K01. I am sorry, it's not K01 over here. It is K10, right? So instead of K10, right? So at every point there is a possibility that the prover may escape if the verifier decides to go the other way. In fact, for the prover to be caught through his series of lies, at every stage, right, at every level, the verifier has to guess the correct way where he lied, right? And up to the root, up to the leaf. So he has to go all the way down, and then he can possibly be caught. Right? At the base case, it will probably boil down to verifying whether a certain assignment is a satisfying assignment or not a satisfying assignment. At which point the prover will be caught. Right? But then, so there is a probability of the prover getting caught, but if the prover does this strategy, like lying only in one of the two options at every step, the probability of the verifier catching him is at most 1 divided by 2 power n, right, which is what I have written here. So the prover can try this very evasive strategy and almost never be caught. So the completeness is fine. All these protocols that we have been discussing so far, whenever the prover wants to convince the correct thing, the honest prover will always be able to convince with probability 1, so with perfect completeness. But the soundness is a problem here. The evasive prover that we just described gets accepted with the probability of 1 minus 1 divided by 2 power n, and this is very high. This is way high. It's too close to 1, so this is not really going to help us. So we want to, so this gap of 1 and 1 minus 2 power n is too close. We want to do something else. So we'll do something else completely different, or roughly in this template, but then we'll bring in a new ingredient which is completely different. So we'll use polynomials. So given phi, which is a Boolean formula, right? So variables, negations, and or etc., we will first write down a polynomial called p phi, okay, with the property that the polynomial will have n variables x1 to xn, the same looks like the same as the Boolean variables x1 to xn, with the property that whenever x1 to xn is from the Boolean hypercube, meaning whenever x1 is 1, x is from the 0 1 power n, right, whenever, so this denotes x bar denotes, sorry, this x bar denotes x1 up to xn. Whenever x1 up to xn is from a 0 1 case, in that case, if you evaluate this polynomial, it will be the actual the truth value of the Boolean formula. So p phi of x bar will be equal to phi of x bar, meaning if x bar is a satisfying assignment, p phi of x bar will be 1, and if x bar is not a satisfying assignment, this will be 0. So it will be 1 or 0 if x bar is a satisfying or not satisfying assignment, right? And degree of p phi will be at most 3m. And further, this polynomial will be very structured polynomial that can easily be computed given the inputs x1, x2 up to xn, right? Or even given alpha 1, alpha 2 up to any integer input also, this can be efficiently computed, okay. So in fact, we have seen almost the same technique when we saw the parity in AC0 proof, not in AC0 proof by Razborov and Smolensky in lecture 41, right. So you can go look up those lectures, but there I think it was for a specific field, but the idea is exactly the same. So how to construct p phi given phi? So what would phi have as its components? So it could either have constants 0 or 1. We could use the same constant 0 or 1 in the polynomial. We could have variables xi. We will use Boolean variables xi will be replaced by polynomial variables in the polynomial xi. When there is a negation of a variable, okay, like it is denoted neg xi or xi bar, we can use 1 minus xi, meaning when xi is 0, 1 minus xi is 1, when xi is 1, 1 minus xi is 0. When we have an AND of two formulas, psi 1 and psi 2, then the resulting polynomial will be the product of the two polynomials, right? So because when psi 1 is 0 and psi 2 is 0, the product is 0. When either one of them is 0, the product is 0. When both of them are 1, the product is 1. So when either so the product replaces the AND. So OR, how to represent OR? Well, we have the De Morgan's laws, right? So we have the De Morgan's laws. So we have psi equal to psi 1 or psi 2, right, which is actually psi 1 negation and psi 2 negation, the negation of the whole thing, right? This is the De Morgan's law. We use exactly this because we have already seen how to deal with negation and how to deal with AND. We could just use both of that. So we negate p psi 1 and p psi 2. So with 1 minus p psi 1, 1 minus p psi 2, take the product and then negate it again. So 1 minus this entire thing. So this is the OR. So what do we have at the end? We have, if you do this operation successively, basically we take a clause is an OR of three things, we use this operation, and then an AND of everything. So it's just take the product of the clauses, right? So we get a polynomial, and the degree is 3 sat instance, so 3 CNF. So each clause will be represented by something of degree 3, and suppose there are m clauses, the final polynomial will be 3 multiplied by m. So degree of the final polynomial will be at most 3m. Okay, so this is what we have, and it should be fairly clear from the construction that whenever the inputs x1 up to xn are from 0 and 1, the polynomial evaluates to 0 or 1 depending on whether x1 to xn, that particular assignment is a satisfying assignment or not. So whenever x is from this, the polynomial evaluates to 0 or 1. So, and this is a very easy computation, the derivation of this polynomial. Both the prover and verifier could do this independently, right? It's not something that is very difficult to do. And now the goal is, instead of checking the number of satisfying assignments of a Boolean formula, we could just say that out of all the possible x1 up to x1, x2, x3, etc., taking values from 0, 1, we just want to sum the polynomial evaluations at these two power n values, right? Because the evaluations is just simply 0 or 1, depending on whether they are satisfying assignments or not. So we just want to see whether the sum of this is equal to k, right? So instead of the Boolean formula deciding whether the Boolean formula has k satisfying assignments, we want to take the sum of the polynomials at these 2 power n values, 2 power n assignments. And this protocol is called sum check protocol, where we will do this. And moving to polynomial gives us some additional advantages, as we will see in this protocol. So we will define a new polynomial called on single variable x. Okay, so we will call it hi of a1, a2 up to ai minus 1 of x. So what is this? So think of the p5 polynomial. Suppose all the I minus 1 variables are fixed. First I minus 1 variables are fixed to a1, a2 up to ai minus 1. Okay, the I minus 1 variables are fixed, right? And the ith variable is the free variable x. Okay, so that is what the same x over here in the left hand side in the argument of hi. And we want to find out how many, we want to find out the sum once we fix a1 x1 to xi minus 1 as a1 to ai minus 1. We want to find the number of, or we want to find the sum of the polynomial ranging where i plus 1 to xn are chosen from the 0, 1 values, right? So it's exactly whatever it's written here, so it may be a bit difficult to describe. The key thing is that the first I minus 1 variables are fixed. The I plus 1 to n variables, we just sum it for all possible combinations, 0, 1 combinations. So it just becomes a polynomial on x, a single variable. Okay, so the ith variable, so that's why it's called hi. Okay, so the x corresponds to the ith variable here, right? So it's a univariate polynomial in x, and this will play a crucial role in the protocol that is going to come up. So earlier, right, the verifier asked for hi0 and hi1. In other words, it's what I mean is, so maybe it's like what is h10 and h11, right? So what is h1? So h1 does not have any other a0 or anything because it is from a1 to ai minus 1, so there is nothing. So h1 of 0 is simply you sum up over all xi's from x2 to xn. So basically you sum up over everything x2 to xn, and so sum up over x2 up to xn from 0, 1, p5 of 0 x2 to xn. So it's, in other words, we are asking how many satisfying assignments are there where x1 is fixed to 0. So this is actually k1, sorry, k0. Similarly, h11 is k1. So earlier we asked for k0 and k1, which is h10 and h11, and then we chose one of them to verify, right? So the problem was we chose one of them to verify, and there were way too many options for the prover to escape. So what we will do here is not ask for h10 and h11. Instead, we will just ask for the entire polynomial h1x. Okay. So notice that p5 is degree at most 3m. So h will be also of degree at most 3m. In fact, if you consider xi and make some simple assumptions, you can say that, in the sense that if xi appears only once in a clause, at most once in a clause, then the degree of xi will be at most m, right? Because it can appear at most it will not appear twice in a clause. It doesn't make sense for a specific variable to appear twice in a clause, right? So the individual degree of any variable is m. So in fact, the degree of hx will be of at most m, right? So instead of asking for the evaluations at 0 and 1, why not ask for h itself, the polynomial hi itself, right? So the point here is that hi is a degree m polynomial, so which means the prover will have to tell the entire polynomial. So one way to describe the degree m polynomial is to give the m coefficients or m plus 1 coefficients, constant term, degree 1 term, degree 2 term up to degree m term. And so what is happening is that the prover is giving out much more information than just 2 evaluations. So he has to commit to a lot more information, and this makes it difficult for the prover to escape like in the previous situation, right? And what we will do is also we will work to make things simple to limit the size of the numbers. We will work in a big field, a finite field fq, where q is a prime that is like that is around 300 mn. Okay, in fact even 100 mn may be enough. Okay, so we will choose q to be a prime of this size, roughly this size. So let me say roughly this size, so that this will be large enough so that there is no this will be large enough to perform the computations. At the same time, this will give us this will not blow up the size of the computations. Okay, so maybe let's try to see the protocol once again. So verifier asks what is h1x, which I have already described, right? h1x. So h1x is simply the summation over x2, x3 up to xn, where the first variable is capital X and the rest are ranging over 0, 1, right? So you take the sum. So now the prover will want to lie, but now in this case, unlike the earlier case he had to provide k0 and k1, but now he has to provide a polynomial, right? So perhaps he could still be smart and provide a polynomial. So let's say he returns some polynomial, let's say g1x, and where g1 need not be same as h1. It need not be same as h1, but he could be smart enough and craftily produce g1 such that g1 of 0 and g1 of 1, if you sum them, it will add up to k. Okay, so prover could craftily create g1 such that g1 of 0 and g1 of 1 will add up to k, because this is the next thing the verifier is going to check, right? Whether so g1 is the number of g1 of 0 is the number of satisfying assignments where x1 is 0, and similarly g1 of 1 is the number of satisfying assignments where x1 equal to 1. So he is going to check whether g1 of 0 and g1 of 1 add up to k, right? So let's say prover is up to this task and produces g1 carefully enough, right? Okay. Suppose the verifier is trying to be honest, then there is no problem. The verifier can he can give the actual h1 h2, sorry h0 h1, right? But the problem arises when the verifier is trying to fool the prover, when the number of satisfying assignments is not k, right? So he could craft g1 such that g1 0 and g1 1 add up to k, right? So now suppose the verifier checks and is okay. Now the verifier will want to indeed check whether G1 is the correct polynomial, right? G1 is actually equal to the H1. So this is the rest of the algorithm. So basically it's the same thing. You can think it's a recursion, but just for clarity I will explain a couple of more steps. Okay. So okay, there is one more aspect that I have not mentioned, but I will mention it now. So instead of asking G1 0, G1 1, right? Now verifier needs to check whether G1 is indeed H1, right? So what verifier does is pick an A1 from the field. The field contains not just 0 and 1, right? It has q elements, fq, so 0, 1 up to q minus 1. So verifier picks A1 from this field at random. The verifier computes G1 of A1, okay? And let's say verifier sends A1 to the prover. Now the prover has to send, so asks prover to give this means the protocol, once it's established, which is established even before the polynomial or anything, the prover knows to send this h2 a1 of x, meaning a1 is fixed, the second variable is the variable, and x3 to xn is the variable over which the summation will range. So prover has to provide h2 a1 of x, right? So what is h2 a1 of x? Sorry, p phi, okay, summation of x3 up to xn, p phi of a1 x sorry a1 x now x3 up to xn. Right. So prover has to give this polynomial, right? So suppose prover gives a polynomial g2x, right? Now the verifier has already or can already compute g1 of a1, and you can verify that g2 of 0 and g2 of 1 should add up to give g1 of a1, right? So this is an important identity, because g2 of 0 and g2 of 1 should give you whenever a1 is fixed, it should give you the summation, it should give you g1 of a1, right? So this is because, maybe I'll just say one more line, since h1 of a1 is equal to h2 a1 of 0 plus h2 a1 of 1. Because g1 is pretending to be h1 and g2 is pretending to be h2 a1, this has to be true. So verifier checks this. If equal, fine, right? If not equal, he can reject it right there. If equal, he picks a2 and computes h2 a1 of a2, right? Sorry, not h2. He does not have h2, he computes g2, sorry, he computes g2 of a2, right, and asks prover for h3 a1 a2x, and the same cycle repeats. So every time the prover has to, so the challenge here is that every time the prover does not know which is the random value that is chosen from the field, right? So the prover can possibly engineer, so as I said before, G1 could be engineered in such a way that G1 0 plus G1 1 equal to k. But then he is already committed to the polynomial G1. Now verifier is coming up with a random value A1, and the prover has to, or the prover, in order to convince the verifier, the prover has to make sure or that G1 of A1 is equal to the correct value of H1 of A1. But if G1 is equal to H1, right, then it will automatically be ensured. But when G1 is not equal to H1, right, suppose when the number of satisfying assignments is not K, and if the prover has been crafty in making the polynomial G1, he cannot, the point is that two different polynomials cannot coincide on too many values, right. We have already seen this in polynomial identity testing, I think lecture 43, 44, something like that. The number of given f and g, the number of points on which f and g coincide is at most the degree, right, because f minus it has to be the root of the difference polynomial. So there are only so many points where they can coincide, and we have chosen the field to be large enough so that most of the points, the number of points available are way more than the number of points where they can coincide. So if A1 happens to be a point where G1 is not equal to H1, then the prover is doomed. And even if the prover gets lucky here, and G1 A1 is happens to be a correct, if the prover gets lucky here, even then potentially he could be caught at the end, because I think if the prover gets lucky here, he may get escape, but then that is accounted for in the probability. Okay, right. So the point here is that the probability of the prover getting lucky is very small, right, and at each stage, suppose the prover does not get lucky, suppose G1 A1 is not equal to HA1. Now again there is the prover has to kind of lie to and create another polynomial to make sure that it matches up with this, right, to keep up with this lie. So it's like this philosophical thing where sometimes when it's better to tell the truth, because if you tell a lie, then you have to make another lie to cover up for that, and then another lie to cover up. So you have to keep lying up one after the other, right? And so there's a lot more work going on there. So it's the same thing over here. So if G1 A1 is not a good, G1 A1 is not equal to H1 A1, then the prover has to continue lying. So at every stage, the probability of him escaping is very small, right? And at the end, the verifier will just check whether Gn minus 1 An minus 1 is equal to Gn0 plus Gn1, which is just like what we did above, right? Same thing over here. And if they are equal, it will also, the verifier will pick An at random and check whether, finally just a complete check, Gn An is actually equal to the polynomial value, right, evaluated at A1, A2 up to An, right. And if all of this is fine, then the verifier accepts, else it rejects, else the verifier rejects. Okay, so the proof, how many rounds, maybe n or n plus 1 rounds, and at each time the prover, the verifier is simply sending, the only thing that the verifier needs to send is just the random bit A1, A2 and so on. Nothing else is needed to be sent, because the verifier knows, the prover knows that the verifier is asking for this polynomial H1, H2 and so on. Okay, so the key thing here, so the efficiency is, okay, let me just come to the efficiency first. Verifier just receives a polynomial of degree at most m and has to perform just 3 evaluations at 0, at 1 and at the randomly chosen value at A1, A2 or whatever, the ith stage AI, right? And we have already assumed that or we have already seen that the polynomial is something that can easily be evaluated. So this is an efficient process, deterministic polynomial time process. And completeness, if the number of satisfying assignments is actually k, that means the polynomial sum of the polynomial over these 0, 1 power n points is also k, then the prover just acts in all honesty, right? Every time he just outputs whatever is asked for by the verifier, and the verifier is convinced. So perfect completeness. There is no possibility of him not being accepted, the proof not being accepted. So the completeness is perfect, 100%. What about soundness, right? So this was where we faltered last time, where we saw that the probability of acceptance was still very, very close to 1 minus 1 by 2 power n. So the number of satisfying assignments is not equal to k, then the prover has to lie at each stage, right, and hope that he does not get caught, right? And the point here is that at each stage he is providing an entire polynomial and not just two values. So in the earlier attempt we saw that if he provides two values, it is easy to kind of slip away and the verifier not being able to catch the prover. But when you are providing the entire polynomial, the thing is that he is likely to be wrong in most of the values. So it's a very, very, very good chance that the verifier will go to a point where the prover is did not get lucky, right? So then he has to repeat the lie, and then he has to repeat the lie again, right? So what is the probability? So we are interested in, suppose x not equal to L, or suppose number of satisfying assignments is not k. What is the probability that the prover will get lucky, or right? Or what is the probability that prover will not get lucky? So so let's just consider the step 1, and this will be easy enough to calculate. Prover has to send G1 such that G10 plus G11 is equal to k, right? This is what he had to send. So if the number of satisfying assignments is not k, prover has to lie, and he cannot send the correct h1, right? Because if the correct h1 is sent, h1 of 0 plus h1 of 1 will not be equal to k. It will be the correct number of satisfying assignments, right? So he has to lie. So he gives a wrong G1. This means that now the verifier is going to choose a random A1, and at this value, at this A1, it's very unlikely that G1 and H1 coincide. So why is this? So what is the probability that G1 A1 equal to H1 A1, where the probability is over the choice of A1? This is M, because M is the degree of H1 and G1, because the number of places where they can coincide is at most the degree. Number of places two distinct m degree polynomial can coincide. This is at most m, because they are degree m, they can have at most m roots. And the choice of A1 is over q values. Fq has q values. So the probability of the prover getting lucky is m by q. So this is the probability that he gets lucky in round 1. With probability 1 minus m by q, he is not going to get lucky, right? And at each stage, right, there are n stages, because there are n variables x1 to xn. What is the probability that he gets lucky? It's at most m by q. So what is the probability that he gets lucky in any of these stages? So one is the union bound. So one way is the union bound. So he gets lucky in round 1 or round 2 and so on. So there are n rounds, so the probability is at most n times m by q. And if you remember, we chose q to be something like 300 nm, I think, something like this. I think 100 nm would have sufficed, but so basically this fraction becomes something like 0.01, some very, very small quantity. So the overall, so this is the probability that the prover gets lucky in any round. This is an upper bound to that probability. Right? Only then can the prover succeed. When the number of satisfying assignments is not k, what is the probability that the prover gets successful? It is something like 0.01. So this is something very close to 0. So the soundness is good here. So it is less than one third or whatever as per the definition, right? So that's the proof. So we have shown that by this protocol, sum check protocol, the prover can convince the verifier, there is a protocol for a prover to convince the verifier that the Boolean formula, given Boolean formula, 3C in a Boolean formula has at most or has exactly k satisfying assignments. And if it is not the case, if the formula does not have k satisfying assignments, if the number is different, then there is no, even an all powerful prover cannot really help to convince the verifier, right? Because the probability by which he can convince is going to be small, right? So some remarks. One is that I mentioned already. At every stage, the verifier just asks for just sends the random information. So verifier sends A1 at round 1, right? And verifier sends A2 at round 2, and because the prover can compute everything else, prover can compute G2, prover knows that verifier is asking for H3, A1, A2, whatever. At each step he knows what is being sought, what information is being sought. And so the prover, the verifier, all he needs to do is to send the random coins. So it's a completely public protocol, public coin protocol. Just that it's not like all the random coins are there up front. So suppose all the random coins were there up front and the prover knows these random coins, then it is possible that the prover will make the polynomial according to these random choices, in which case it's not really random, right? So the prover knows this and then engineers his polynomial so as to succeed. But that's not the case. The prover commits to a polynomial G1 and then comes A1. Then prover has to commit to G2 and then comes A2 and so on. So the verifier is tossing coins and sending. So even though the random coins are public, the random coins are being generated only as and when required. And this is what is helping, or this is what is keeping the prover in the dark. And now he has to commit to something that he has no clue of. And this is making him falter with a big probability, right? And so Sharp 3SAT is a Sharpie complete language. So this implies that P to the Sharpie is contained in IP, because Sharp 3SAT is a Sharpie complete language. And we have already seen that IP is contained in P space in the previous lecture. And it is actually true that IP is equal to P space. This was a proof by Lund, Fortnow, Karloff, Nissan working together. And at the end, Adi Shamir just completed the proof, building on top of a lot of work that was built up by Lund, Fortnow, Karloff and Nissan, proving IP equal to P space. How does the proof go? In fact, the proof, it's very much like what we have seen here. So it is exactly like this, just that the polynomial has to be a bit different, because we are dealing with P space. Now it's not just a 3CNF formula, it also has a quantified formula. So how do we deal with quantifiers? How do we get a polynomial that corresponds to the quantified formula? So in addition to these things, in addition to having how to deal with negation and or etc., we also have to deal with there exists and for all. We can do something like and or. So for exists can be thought of or, universal quantifier can be thought of as and. But what it does is, this results in a polynomial of huge degree, and this huge degree is not something that we can work with, because so here q was 300 mn, so which was fine, because every field element could be sent easily, and not just field element, even the polynomial only q number of elements needs to be sent. So all this is fine. Whereas when the degree is large, it becomes very difficult. Like the degree itself is exponential, then exponentially many terms need to be sent. Right. So that is the main bottleneck for the proof that IP equal to P space. And what is done is a multi-linearization trick. So because we are working in 0, 1, it was observed that x squared is equal to x for 0, 1. So x cube is also equal to x, and so on. So whenever there are terms of individual degree greater than 1, it can be reduced to degree 1 terms. And this operator needs to be integrated with the proof to get the polynomial of a sufficiently low degree. And this needs to be repeated every time some other operation is done. Apart from that, it's roughly the same roadmap, and if you're interested, you can read the paper. And as I said, this is a public coin protocol, right? And I said that they both do it over some prime field. So once they know x, or once they know the formula, for instance, the prover can help, because he is all powerful, he can help choose a prime number that is roughly of the correct size and send to the verifier, and the verifier can verify. So prime numbers can also, verifier can also decide that it is a prime number at his end. He can use a deterministic or randomized prime number algorithm to check that it is indeed prime. Right. So prover sends a prime number of the appropriate size, and the verifier verifies, and then they agree to work on that prime number. Right. And all this this has an interesting history. This theory developed starting from the early 80s, 82, 83 or something. And there is an article, somewhat informal article called A History of the PCP Theorem. This article is by Ryan O'Donnell. It's not explicitly mentioned by Ryan O'Donnell or something. Just Google this title, A History of the PCP Theorem. It's an article, it's a 10-page article, but it's a lot of photographs of all the parties involved. And interestingly, all the photographs are of those times, at the time where they, now these people may be older, so this is at that time, 80s, late 80s. It's an easy read, it's not much technical, it's mostly informal. So who proved what at what time, and then some set of people proved this and somebody else proved that, and so on, how this built up over a bunch of over a period of over the years. It's a very interesting article, so I suggest you have a look at this. So PCP stands for probabilistically checkable proofs, which is something that was very important which played an important role in complexity theory, which evolved from interactive proofs. So that's another interesting offshoot of interactive proofs. And yeah, I think that's all I wanted to say in this lecture. So just to summarize once again, we wanted to have an interactive proof for sharp 3 set. Right? So given sharp 3 set, given a formula and a number k, we want the prover to convince the verifier that this formula has k satisfying assignments. So we saw a couple of wrong attempts, and then we modified our approach. So first we made a polynomial p phi that has a same 0, 1 value as phi when phi is given a Boolean input, right? So p phi also evaluates the same value as phi over Boolean inputs, right? And p phi was also easy to evaluate, and small degree. So this trick is called arithmetization. Maybe I should say that somewhere here. So this is called arithmetization. So Boolean formula is converted into an arithmetic formula with numbers. And we explained how to construct this. And then we explained the sum check protocol, where we have the the verifier send a random a field element at each round, and the prover has to make sure that or prover has to hope that at this field element his polynomial will evaluate to the correct value. So there is a probability that the prover will get lucky, but then this probability can be upper bounded, because at each stage the probability of him getting lucky is small. So overall the probability of him getting lucky is also going to be upper bounded. So there is a significant probability of him not getting lucky, and whenever he does not get lucky, he will be caught out at the end. Right. So instead of the main idea is that instead of just asking for two values, we make the prover commit to a polynomial itself. So which is like degree d or m values, right? M degrees. So now he may engineer the polynomial in such a way that it works out correct to be in 0 and 1, but he cannot do that for all the values, and nor can he give the correct polynomial, because if he gives the correct polynomial, he will be caught right at the beginning, right? Because at 0 and 1 itself, it will not give you the correct values. So there is a limit to how much he can lie, and the probability of him being able to lie is upper bounded by mn by q, which is something like 0.01, which is way less than 1/3. Right? So it's not less, it's way less than 1/3. And this shows that there is an interactive proof system for sharp 3 sat, which shows that sharp p is contained in p space, sharp p is contained in IP, and we also said that IP is equal to p space, without, and gave a very high overview of the proof, which roughly follows the same roadmap, but some additional ingredients are required. And yeah, that's it. Thank you.